Hello, everybody. My name is Logan Brown, and I'm a junior biochemistry major here at UNCG in the Department of Chemistry and Biochemistry. And I work in Dr. Mitchell P. Croat's Organic Synthesis Laboratory. And today I'll be talking to you about the synthesis of isomaleimide and its reaction with Danishefsky's diene in the Diels-Alder fashion. So first, I'd like to talk about what is the Diels-Alder reaction. And before we even talk about that, I should introduce what organic molecules are. And organic molecules are molecules composed of carbon, and they're represented in these drawings at every joint. So every joint that I'm circling here are carbon atoms. And we know all life on Earth is composed of these carbon molecules, or these carbon-based organic molecules. And so the Diels-Alder reaction is a diene plus a dienophile, the dienophile and the diene, to create a cyclohexene product, or this hexagonal ring. And it's a pericyclic reaction with a concerted mechanism. That basically means that the bonds that are between these carbon atoms are simultaneously broken and reformed in a pericyclic transition state. That just means that the transition state resembles the ring, and then the ring is formed. It's also known as a 4+2 cycloaddition. That just means that we have a 2-carbon compound plus a 4-carbon compound, and we create a cycle or a ring structure. And this reaction was discovered in 1928 by Otto Diels and Kurt Alder. And the substrates that we are working with on this project are isomaleimide and Danishefsky's diene here. And I've circled the analogous structures, the dienophile over here and the diene here. And how do we make this chemical reaction work? Well, I like to draw the analogy to cooking soup. We get a pot, we combine the first ingredient and then the second ingredient. We mix them together, and then the product that remains is going to be our hexagonal product. But why is this important? So the significance of the Diels-Alder reaction allows you for the synthesis of complex molecules through the creation of carbon-carbon bonds. And creating carbon-carbon bonds is something that is very valued in organic synthesis because it allows you to build larger, more complex structures that could potentially be modified into drugs. And some examples of these drugs developed through the Diels-Alder reaction is cortisone, which is a hormonal drug for arthritis, allergic reactions, and other skin conditions. Taxol, or better known as paclitaxel, which is a discontinued drug for cancer. Cholesterol, everybody knows cholesterol. Synthetic cholesterol is created using the Diels-Alder reaction. And tetracycline, which is an antibiotic for acne and other various infections like syphilis. And this project aimed to show that isomaleimide, which was created in a unique one-pot synthesis technique developed by the Croat lab, has the potential to be the precursor to these synthetic scaffolds through the Diels-Alder reaction. And I've shown here in red those hexagonal shapes created by the Diels-Alder reaction, like I showed on the previous slide. So what did we do? Like I said, this is just like cooking a soup. Our one-pot synthesis of isomaleimide, we took our first ingredient, we took our second ingredient and stirred it in some liquid for 30 minutes. And then we took our fourth ingredient and added our fifth ingredient, stirred those together for 15 minutes. And then we strained them. We got rid of the liquid. If you think about it like straining your vegetables, we got rid of the liquid and the solid that remained was isomaleimide. And then we wanted to react this in the Diels-Alder way. We took the isomaleimide, added it to Danishefsky's diene, heated it up to 100 degrees Celsius and just stirred it for a couple hours. And then our product was formed, and you can see I've highlighted in red again, that red hexagonal ring that was created by the Diels-Alder reaction. And so this worked. In conclusion, the synthesis of isomaleimide was very easy and user-friendly. And reacting with the Diels-Alder reaction was successful. We were able to find proof that the reaction had worked. Methods to purify the product and avoid decomposition are still being experimented with today. And I'd like to thank Dr. Mitchell P. Croat, the Marie Foster Rourke Distinguished Professor of Chemistry. He is the principal investigator and he runs the lab that I work in. Dr. Khairul Alam, he is the project head and designed the project. Dr. Franklin J. Moy, who is the Nuclear Magnetic Resonance Laboratory, he runs that downstairs. And Dr. Daniel Todd, who runs the Mass Spectroscopy Laboratory. So thank you for coming and listening to my IRCA presentation. I hope you enjoyed the rest of your conference.